Thank you for inviting me here today, and I think it's interesting to speak right after Cliff because I think some of the issues that he's brought up will resonate with what I'm talking about when we're discussing geospatial data. As I worked on the talk, I realized that it would be broader in scope than simply the social sciences as noted in the title. Spatial data is used in much the same way across a wide array of disciplines. The questions may vary, but the underlying issues a researcher faces is often the same. Given that, I'm going to provide you with some examples from a range of different research projects. First, I'll give you a quick introduction to geospatial data, what it is and how it's changing. We're going to look at a variety of collections issues affecting research. I'll discuss the rise of external data sources and their impacts, and finally, the role of libraries in the management of data in-house to mitigate some of the issues that are raised today. I want to take just a few minutes to introduce or expand your knowledge of geospatial data in order to give everyone a baseline understanding of these resources. So geographic data has an explicit geographic positioning that ties it to a place or region on the Earth. And this is typically done through geographic coordinates such as latitude or longitude. The data model the world in a way that breaks down information into thematic components such as imagery, elevation, addresses, and boundaries that allow for querying and analyzing between the layers once they're properly aligned. So I'm a big lover of cake, and I think of it as a cake where you slice down through the different layers to understand the information about the Earth. So one class of data is vector-based. Vector data is expressed as points or lines or polygons. Points can be things like cities over 100,000 people that are shown as dots. Lines could be transportation routes or oil pipelines or river networks. Polygons may be county boundaries, water features, or voting districts. So when you look at a digital map like this, say Google or Apple Maps, you see what appears to be a single layer of information telling you about a specific place. But in reality, it's a series of data layers that change as you zoom in and out of the map depending upon your scale. Here you see the map is actually made up of a series of layers. So road and transportation networks, points of interest, green space, and water bodies. As the information on the ground changes, these data layers can change to reflect what you're seeing on the map. Raster data contains continuous information in a grid pattern of pixels with the specificity of the information governed by the pixel resolution. So here you see two images of Chicago at different resolutions. While they appear to be photographs, they're actually not. They're layers of information from different bands that are combined to give you what you would call, say, a real-world look at the ground from these images. So you can choose which bands to combine or to read, and you can reveal different kinds of information from looking at those bands. So at the top here, you see a chart that shows the wavelength bands for capture of high-resolution small satellites, which is at the very, very top left. That little tiny two-band thing show the small sats and CubeSats. We'll talk about that a little bit more later. But you can also see medium resolution Landsat and Sentinel satellites, which is that big bottom gray area that you see. So at the bottom left, you see Mount St. Helens, and I'm only showing you the infrared band here, and that infrared band is vegetation. So anything that shows up red in that little image down there is vegetation. On the right, I've chosen different bands, and they show snow and ice in blue and clouds in yellow. So data such as these allow researchers to study things like deforestation and crop yields, or the rapidity of ice melt in the spring. So how do we collect these data? They're collected in numerous ways through things like GPS devices or satellites, or through passive sensor surveys. They're also created actively through things like the Census Bureau research or perhaps direct observation. So geospatial information is used to answer a broad array of questions, everything from emergency preparedness to healthcare, from environmental impacts to the movement of people and things. So collections issues play a big part in spatial projects and have large impacts on the researcher as they go about their work. How collection of data happens has changed a great deal over the last decade, and it's going to continue to change and evolve rapidly. So geospatial data are often produced by government agencies at all levels, especially base level data such as boundaries or road networks or thematic layers about housing and health and natural processes. Often this content came to our libraries through depository programs from state, federal, national, or international programs such as IGOs and NGOs. Much of that data, which you can see we used to get on CD-ROMs or DVDs, is now going to websites that allow people to download the data directly. It makes it harder to find for the researcher, and persistence becomes a problem as the host can remove the data at will. Libraries now must actively seek out, capture, and preserve the content their researchers need. Finding and retrieving data is often the most time-intensive part of a geospatial project. In the United States, we're used to high-quality federal government geospatial data being in the public domain. This is rarely the case outside the United States. In order to get high-quality geospatial data for research, one must buy it, and it's expensive. This is not surprising because data collection, the effort to do it is time-consuming and it's hard. For example, you can see at the bottom, a single layer of villages in a country can cost nearly $25,000 with academic discount, and that's for one layer of information. Oh, let me go back one. So OpenStreetMap, which some of you may have heard of, was conceived as a way to provide free base-level road and building data with a worldwide scope through crowdsourcing. But the data quality depends very much upon where you're looking. For example, the data of Haiti is very good due to the intensive focus on it after the earthquake and hurricanes. While the road network in Bangladesh is quite good, the identification of buildings is not. In many developing nations, there is no commercial motivation to map streets or buildings, creating the need for researchers to purchase high-quality data rather than using an open-source data avenue. Over the years, I've seen faculty greatly reduce the scope of their research due to the cost of procuring data. For example, an anthropologist searching for hominid bones in the Rift Valley of Kenya kept constricting his field area until he was able to get the imagery he needed at the price he could afford. Libraries and librarians in positions such as mine judiciously purchase only these data that have a broad use for people. We can't underwrite the purchase of highly specific data for individual projects. We simply don't have the budgets to do so. So licensing presents many challenges to researchers and libraries, and we've talked about that already here. High-resolution satellite imagery companies now routinely create platforms that give access to content through a license. Recently, we began negotiating with one private satellite company to gain institutional access to their imagery. We were just told, and I found this out about a week and a half ago, we were just told the company is legally restricted by the federal government from providing imagery to citizens on a list of specific countries. So how do we as a university deal with this? If we license the resource, are we obligated to police the students or faculty from those countries to know if they're actually using that data set or not? How would we do that? This may mean we can't provide a university-wide site license to these data. Instead, each faculty member may have to request imagery on a case-by-case basis and negotiate directly with that company. For-profit companies are often reluctant to provide raw data to the researchers, either directly or mediated through libraries. They want the researcher to use their platform, which leads to questions such as what the companies are doing with the information they glean from the questions being asked of the data. The researcher, in effect, as we know, is becoming the product. There also may be onerous terms for the contract that impel researchers to comply with unworkable terms. For example, Stanford recently rejected a contract for Elsevier's Reaxys product due to the unacceptable license conditions, such as their requirement to see drafts of papers before publication. I recently negotiated a contract for historical boundary data from a European data producer for a political scientist researching historical voting patterns. The provider wanted to review all of the manuscripts before the publication and required the user's contact and get approval before altering any of the geospatial information. After much negotiation, these provisions were stripped from the contract and we were able to sign it. Licensing practices for spatial data are complex, and often numerous different licenses will come into play in the same research project because the layers are coming from different sources. So let me give you another example from data available through OpenStreetMap. While the availability of this data set can make it easier for researchers to acquire what they need to do their analyses that they want to do, it comes with an added complication of licensing requirements that are not well understood by many of the researchers using the data. OpenStreetMap makes their data available through an Open Data Commons license that includes a share-alike provision. This means that if a researcher combines these data with data from another source to perform an analysis, the new data set needs to be provided under this share-alike license as well. If the project involves sensitive data or subject matter that are not allowed to be or are best not shared publicly, like information about human subjects or international conflict areas or endangered species, this sharing will not be possible, which means that OpenStreetMap data can't be used. It's becoming more important for us as librarians to insert ourselves into the research processes of people early on so they understand the implications of data before using and embarking on a lengthy analysis that ends up being a waste of valuable time because they're unable to publish their results. This recently released report created by Kevin Pomfret, who's on the National Geospatial Advisory Committee with me, is an excellent primer for researchers and librarians who deal with geospatial data. It's written by a lawyer for non-lawyer and clearly explains the intricacies and pitfalls of these data licenses. I highly recommend you take a look at it. Data currency is an issue when it is provided by a third party and not captured locally. We've talked a lot about that in the last day or so. Often producing bodies, both nationally and internationally, will keep only the most current layer about specific themes, say educational institutions. It becomes difficult to know when the layers are released, do longitudinal studies, or to reproduce results in the future. More on some possible solutions on this later. Privacy issues have been in the news a great deal lately, and often geospatial information is part of this discussion. Geospatial data have the ability to turn implicitly or indirectly identifying data into explicitly identifying data when combined with other data sets. The use of artificial intelligence and algorithms. Let me give you an example. So here you see data from Strava, a company that makes an app called Run, Ride, or Swim. You may have this on one of your smartphones. It tracks your workouts and allows you to analyze them from day to day. Last November, Strava released a new heat map with aggregated information from 1 billion activities from people using fitness trackers. An Australian international studies student, Nathan Russer, started creating maps from the data by combining it with satellite imagery on Google Maps and publishing his findings to Twitter. What he and others found, once they saw what he was doing, they replicated what he was doing, were things like military bases. The military was giving fitness trackers to people so they would get out and do more exercise, not really realizing people were wearing these all day when they were awake. So here you can see one of the maps he made. On the top, you can see a CIA base in Djibouti. And this was known. This was a known military base that we have. The smaller bottom one that you can see in the your bottom left, people didn't know about. And this created, as you can imagine, a huge stir in the intelligence community, not just in the United States, but around the world, as these hidden military bases were revealed in many different nations. It was quickly noted that combining these data with other sources, that it's not that hard to identify individuals. So a few years ago, I was working with the Parking and Transportation Department at Stanford to purchase bike data from Strava for Stanford. So Parking and Transportation wanted to understand the bike routes that people use to get to and from campus in order to work more closely with surrounding cities to create bike-friendly commute paths. Had we purchased the data, which we ended up not doing, it would have been pretty easy for a Stanford researcher to match it to a database of employees and students, which they can scrape given that they're inside the institution, combine it with a publicly available address database, and create a database showing exactly who commuted from where and when they were commuting. This is a murky legal area and one that's sometimes addressed through licensing in terms of what can be done with the data to keep individual identities private. Spatial data is becoming increasingly complex and the volume continues to grow fast. Machine learning and computation is making it possible to ask large-scale questions with either huge amounts of current data or time sequence data for longitudinal studies. So you can see on this slide the volumes we're talking about with these satellites. Planet is adding 7 terabytes of imagery per day to their archive. The Landsat and Sentinel satellites are imaging the Earth in its entirety every 3 days. We'll talk more about how this is used for research in just a minute, but let's look at an example of a large vector data set, because this is also an issue. Faculty from Stanford in political science, public health, and econometrics are studying the risks and benefits of handgun ownership in California over the past 2 decades. Specifically, they're working with 18 historical extracts of California voter registration database spanning a period of 2002 to 2016. Registrants' residential location is an important variable, but the address fields are difficult to work with, so they geocoded all registrant addresses, which is 300 million addresses across all 18 extracts. We have one computer at the Stanford Geospatial Center in the library that's set up to run this geocoding service through our ESRI license, meaning the group had to do the computation in our lab at about 1 million to 1.5 million addresses at a run. It took them 4 to 5 days to run the job, with researchers regularly coming in to babysit the machine because occasionally the network would drop and would have to be restarted, or other technical issues would come up and arise, needing staff expertise. This is a brute force method of doing research, but there's no good alternative for our researchers. Stanford offers no way to host this kind of processing in the cloud, nor does Esri allow us, with their license, to put the geocoder in a cloud hosting platform. But this is a common research question. We're typically running these kinds of geocoding jobs in our lab now with the help of our Stanford Geospatial Center staff. One colleague I have refers to this as computing for the vast middle. While the files themselves may not be considered big data in terms of their size, the number of computes needed to do the analysis are big and require more power than a laptop or a desktop computer can handle. This speaks to the need for local high-performance computing platforms and people with computing expertise to optimize these processes. But for satellite imagery, we're now seeing the rise of data-specific repositories. As Jim Gray, author of the Fourth Paradigm, said, quote, "Often it turns out to be more efficient to move the questions than to move the data." And that's what we're seeing more and more. Cloud-based analyses require changes to methodologies and strategies, and libraries are devoting more of our efforts to providing instruction and consulting that support our patron in these tasks. Satellite imagery use is growing as machine learning gets more powerful, allowing for longitudinal studies to detect trends and change over time. Google released Earth Engine in November 2016. They've created a public domain platform to fuse data sources based on co-location on the Earth, allowing researchers to access and query the content using up to 20,000 CPUs at the same time. One of the first research studies published using Google Earth Engine was by Matt Hansen at the University of Maryland, who was studying global forest change by applying algorithms to time series data to quantify global land dynamics. Here's what he states. quote, a total of 20 terapixels of Landsat data were processed using 1 million CPU core hours on 10,000 computers in parallel in order to characterize year 2000% tree cover and subsequent tree cover loss and gain through 2012. What would have taken a single computer 15 years to perform was completed in a matter of days using Google Earth Engine computing, unquote. Earth Engine is being used as a research tool to study crop yields, population changes, assisted driving-based systems in mining, forest clearing, urban wildland interfaces, fire effects on meadows, and more. This is a radical change in the ability of researchers to carry out cutting-edge research, and we're going to see an increasing demand for this access to all these types of resources. Data-specific repositories from Google, Digital Globe, Planet, Mapbox, and Satellogic are providing operable data in near real time with code-centric interfaces for leveraging the data at scale. Planet's pipeline from satellite to browser, so from when it comes down from the satellite to when you can actually use it on their website, is 2 hours. One can track illegal logging, see the effects of flooding, and measure the growth of refugee camps within days, if not within hours of image capture. This is pretty amazing stuff, but it's also worrying at some levels. These are for-profit companies providing consistent access either for free with Google or for a license fee, Digital Globe and the rest, to original research data. It's impossible for our institutions to create persistent access to these resources due to their cost and size and complexity. We have to pay to play in this case. The platforms are not open source. The algorithms in use are opaque. Earth Engine from Google could be gone tomorrow if Google decides it's no longer in their interest to do this anymore. Stace Maples, the head of our Geospatial Center, characterized it to me as research at the whim of Google. And yet, these are phenomenal resources, and at this point, they're irreplaceable. On the plus side, there is an increasing use of self-documenting analysis methods, such as R and Python, where the code is actually the method, and there's a preference for open source and liberally licensed software, which are arguably more within our power to make persistence. So all of this has a role for data management in the libraries. Some large institutions are able to create and maintain institutional repositories, although not all of them are designed to handle geospatial data. Stanford's is, and we work hard at ingesting our geospatial content into it. We do this to provide persistent access to the content we hold and for faculty to deposit their data with us. We have yet to handle large amounts of satellite imagery and have no plans to do so in the near future. Specialized geoportals are becoming more common in the library world. A couple of open source efforts are gaining steam, and through collaborative work, we've been able to provide access to not only our content, provide pointers to partner data as well. In near real time with code-centric interfaces, Stanford has a robust spatial data infrastructure from which content is served out through our specialized interface called Earthworks. This allows researchers to easily locate vector and raster data as well as scanned maps. We actively collect data our faculty and students need, including local and federal government materials. Through Earthworks, we've provided access to over 70,000 individual data layers from 20 institutions. The portal is designed in such a way to incorporate rich metadata about the objects and allow the patron to see content before downloading it to a local machine. Often the spatial data may be downloaded in different formats and streamed directly as web mapping or feature services. The Big Ten Academic Alliance recently released their own geospatial portal. They noted at a recent Geo for Live camp that it has been a success, but that one issue they've had is that it did not ingest local data, government data, they rather pointed to it, only to find that many of these links had changed or the data were no longer available after a certain amount of time. Again, we see persistence cannot be guaranteed without locally storing and serving copies of the content. GeoBlacklight is the open source software running these portals, and I encourage you to explore it more if you're interested in becoming a partner in this endeavor. Throughout all of these processes, it's critical to employ staff that are expert to deal with spatial information. Branner Library houses the Stanford Geospatial Center, and with it 2 geospatial experts, David Medeiros on your left and Stace Maples on the right. They are often full partners in the research projects carried out with our patrons and have both been included as authors in publications. They partner with the faculty and students on data identification and acquisitions, training on software and tools, and project management. They and their library colleagues teach programming and computing skills such as Python, JavaScripting, and R. They're given their time in their jobs to embed themselves in research projects, providing direct support for application development and analysis of results. This hand-in-glove relationship is part and parcel of the research process when using geospatial information. So I would argue that the supply chain for geospatial information is such that it's now integrally fused with the services that must be provided in order for cutting-edge research to be carried out at scale. I'm going to leave you now with one final example of this type of collaboration that's possible when using spatial information. Hannah Binzen-Wild is a researcher in the Stanford School of Medicine. She's working with the Geospatial Center on a project that uses machine learning and satellite imagery to collected and refreshed at a high frequency, in this case, daily. She's trying to identify the locations of active nomadic pastoralist settlements in a region of approximately 10,000 square kilometers in southern Ethiopia. Because of the extremely remote, widely dispersed, and highly mobile nature of these settlements, it's been very difficult for organizations to conduct complete settlement surveys of these groups, resulting in them being missed by most public health needs assessments in the past. The settlements are so temporary because they're nomads that it's impossible for health workers to find them before they move to another location. Hannah's aim is to perform the first randomized surveys of these types of populations in order to provide baseline data for evaluation of future public health interventions with these types of populations. The project required a novel combination of highly recent, high-resolution satellite imagery provided by Digital Globe, cloud-based crowdsourcing, open-source technical infrastructure, and very large screen arrays. The Stanford Geospatial Center was able to perform a full settlement survey in a matter of days, providing the researcher a spatially randomized survey designed and the data to execute that survey in the field. Over 5,000 kilometers of satellite imagery was examined, revealing 225 active settlements, over 3,500 individual huts, which yield 400 surveys, with only 2 settlements having been abandoned by the time the researcher navigated her way into the field. The desire is to apply tools of machine learning for automated monitoring, location, and classification of settlements for future surveys, and to apply these techniques in similar cases in highly mobile and highly dispersed populations in southern Ethiopia, Mongolia, and elsewhere. As a practical matter, this expansion of the project will require the use of cloud-based computing, as the resolution and frequency of imagery updates will make local processing and analysis impractical. The current plan is to create an area of interest, upload new imagery of the area directly into Google Earth Engine for automated identification and classification of settlements on a daily basis. As you can see, projects done at this kind of complexity and scale require intensive support of a sophisticated nature from knowledgeable staff dedicated to supporting innovative research. So in conclusion, I leave you with these thoughts. The nature of research using geospatial data is rapidly changing, with faculty using ever larger data sets requiring sophisticated analysis method and robust computing infrastructure. A broad array of disciplines are incorporating spatial analysis into their research, requiring a flexible support model. We find that scholars are using complex data sources that are increasing in type, volume, and the rapidity of output. Few institutional repositories are capable of collecting and managing the content, requiring use of external data-specific repositories, especially for satellite imagery. To do the most sophisticated research, universities must employ high-level staff with expertise in data acquisition and provisioning, licensing, and end-user support. And while pushing the questions to the cloud creates amazing opportunities, it also raises issues around ownership of the content and the processes and the reproducibility of research. All in all, it's an exciting time for those of us working with geospatial data. While the issues are complex, the ability to understand the world in new and transformative ways has never been greater. Thank you.
Hi, Julie. Thanks for the talk. It was fascinating. I was at the Geo4 Lib camp and saw a presentation on this project. And one of the issues that I don't think you brought up that I think were fascinating to the group there was these communities are in a zone of conflict. And so there was a lot of concern about how you maintain the security of the data. And so I'm wondering if that's something that's come up in the discussions about moving the computation, the research to the cloud.
Yes, thank you for mentioning that. It is in a zone of conflict, and so one of the reasons why all the work was done on the big screen arrays that are held in the School of Engineering that I showed you was so that it was done locally. And when they were doing the crowdsourcing of it, they were only taking small pieces of it and having the crowd help identify what would a hut look like, and then they were bringing that information back in. And it wasn't data that was released quickly. It was released specifically from Digital Globe to the researcher, so it wasn't being made available on a regular basis. But I do think that's an issue that we're going to have to work out with the researcher and with our IRB at Stanford in terms of what's allowed to put in the cloud and what people are allowed to do in terms of using this in places like conflict zones. So I think that's an area of unexplored or constant discussion as you can start to see where issues, if you can get refugee camp information within 2 hours, that's pretty, you got to be careful with this stuff, right? You can't just be cavalier about what these data sources can provide for you.
James Nye at the University of Chicago. I'm bibliographer for Southern Asia. A question that I have for you is about the Compendium on Licensing of Geospatial Information, the UN Committee's report or recommendations, and particularly what kind of role you think CRL or other groups like the Big Ten Alliance might have in advocating with government bodies for use of that as a model. Here I say this based on recent experience negotiating for access to geospatial data from government of Sri Lanka and also being on the edges of discussions for India. And I think there are unnecessary restrictions that might be opened up, but the question for you is really one about the role that CRL might play based on your own experience in negotiating these kinds of rights within the U.S., I gather.
I think it's an interesting area because spatial information, be it on paper or digital, is often considered quite sensitive in its nature. So countries like China or India, when we were buying paper maps from them, we can only buy them at a certain level of resolution. They're considered state secrets. And I think we saw over time when Google Earth was first released, many, many years ago now, what a stir that made, because all of a sudden you had information that was being produced and put out over the internet with countries that had no intention of releasing the level of information and detail that was available then. So I think Kevin's report is actually quite useful to CRL and other groups because in it he explains in quite readable detail what these data licenses can look like and how people should think about it and gives concrete examples. he uses OpenStreetMap as an example of here's what happens if you use a share-alike license. So he not only explains the license, he explains how to think about it in a way that if you create these restrictions, these are the kind of problems that people will run into. So I think it gives us leverage both in libraries and creating, working with people on these licenses, but also it allows us to work with other countries to think about here are some of the issues that come up when you're dealing with geospatial data. I've found that often working with foreign countries that the data producers there, for example, I work a lot with a company out of India called ML Infomap, and they did not work very often with libraries and universities, so they didn't know how to write a data license that would allow us to do things that we would normally want to do with that. And working with them directly, we were able to come up with license agreements that were perfectly workable for universities and for what we needed it for. And so I think this gives us some more leverage to be able to do that. So I think it's helpful to have this kind of report.
So I'm Derek Peterson from the University of Michigan. I have to say I'm pretty deeply uncomfortable with the idea that someone in Stanford in a big screen array, however ethically construed, could study Ethiopian peasants' living arrangements from the Conference of Palo Alto using geospatial imaging and make deductions about it without a kind of intense field work or sort of ethical engagement with people who she or he is studying. I mean, you mentioned, governments like India and China have interests in suppressing the circulation of maps. Other countries have their own statistical bureaus and their own mapping services that are meant to sort of maintain a certain kind of sovereignty over the people who they govern, statistically as much as politically. So I wonder here about, I don't really have a formulated question as much as a kind of feeling of discomfort. It feels to me like a further form of big data imperialism in which people in the global south are being made into subjects of research unknowingly and without their consent and without the government of that represents their interests knowing about it.
I think that's a good point, and one that I have not done a lot of exploration into, so can't speak to that, that exact example directly. I think we see with satellite imagery the ability to interact with the globe in a way that we haven't been able to before. So for example, I've talked to archaeologists who say that high-resolution satellite imagery is being used by people to go out and loot graves. They couldn't see them before, but now that you release this high-resolution satellite imagery, people can actually say, oh, well, this is a pattern of where graves might be, and they're going out and looting them. So you see a lot of issues come up. As a member of the National Geospatial Advisory Committee, we have a subcommittee that is of which we have 2 members of Indian tribes on the subcommittee that are looking specifically at cultural resources in the on tribal lands where people are making FOIA requests to understand where the cultural resources are, be they graves, be they other types of sensitive situations or sensitive areas, and they're looking at policies, federal policies and issues around what does it mean when you get a FOIA request like that. And there are policies around how to deal with them, but are they known by the federal employees that are perhaps down the chain and not the cultural heritage officer? So we're looking at issues like that in our own country in terms of how these things are done. And I think worldwide, this is a real question around what do we know when we can get imagery at this level and who has access to it. And the other thing I think about is not just who has access to it, but if Stanford has the ability, or Michigan has the ability through their university to get access to these data sources, what about other universities that don't have that kind of sway or pull or ability to get access to content? What does that mean about people's ability to do research, and does it attach itself to a specific institution where you're not making things more readily available? So I think there are a lot of issues that come up with this kind of information as well. Not a lot of answers, I guess.
Just a quick question, because I know we're pressed for time. I know that space was opened up in the 1990s to commercial satellite companies, and so what's the balance between commercially produced Earth imaging and government-produced Earth imaging at this point, and is that changing?
Right now, the U.S. government they've put up Landsat, they have Landsat 7 and 8 up. The Europeans have the Sentinel satellites up, and as you could see from my chart, those are mid-range satellites that are up. Landsat 9 will go up in 2020, also a mid-range satellite. They're now looking at what to do with Landsat 10, but I think the governments, I think, are not going to get into this business of the small sats, which is what's really high resolution and quick turnaround. That's going to be left to the commercial sector. As far as I can tell from talking to the people I know at NASA and what they're saying about this, that I don't think that the big governments are going to get into that area. That is going to be left to the commercial sector with this very, very high resolution imagery. It's actually high enough resolution now it can, from space, read a license plate. So, you know, it's pretty amazing and yet scary stuff that's out there. Thank you.